So I think we can start. It's really nice. I'm sitting here because also the people online have to see me. Otherwise, I would be or standing in front of you. So it is a pleasure to guest you in Rome. And actually, it is an honor to have this conference, IGF, here in this prestigious university, which is now my university. So I'm really enjoying this conference for the first time. And I would like to say that we will try to have, apart of the interesting presentation, also a kind of social activities with the gala dinner that I hope you will attend. And you can of course take the occasion to visit the nice city of Rome and look around. So it is a really a great pleasure to have you here as guests. And I hope that if you need help or any kind of support, you can ask to all the people that are organizing this event. That I want to thank for the very strong support that they give you in the organization and the preparation of this conference. It's a pleasure also to introduce two guests that are really strong in research and also friends, and they will be the chairs of this first section of the conference. So I hope that you will enjoy this event, and I hope that the conference will be nice for you, and that you will have a great time in Rome with all of us. So thank you so much. I will not be very long because we received much more submission than what we expect. And so actually we have a tight schedule that we want to respect to go in time for dinner, because as I said before, dinner is also important like a presentation. So we need to attend dinner too. So thank you so much. I leave now the floor to Sara and Chiara that will manage these sessions as the chair. Thank you.
Good afternoon, everyone. I'm very happy to start this session with a talk about gradient deviation thinning process for cell-based treatment of additive manufactured aluminum alloy parts. And just a second. I hope in a few minutes everyone will have the presentation share. Okay. Okay, this work has been performed in our group with contribution of Hassan Haidari, Juan Maliki, Simone Sabazzini, Professor Mario Bagliano, and myself. We all know about the advantages of particle diffusion, the freedom it gives in geometry and design, but there are also some issues that are limiting the performance of additive manufactured parts, including the very poor surface quality, the internal pores, and let's say defects, inhomogeneous my talk, I want to focus especially on the surface state and the problems that are actual parts. There are many different post-processing approaches that are being to address. Because in our research, we are mostly focusing on mechanical surface treatments and especially on shot peening. Shot peening, as you may know, is a classic mechanical surface treatment in which small media are accelerated to impact the surface and induce severe plastic deformation on the surface layer. We have performed shot peening on these samples. The results have been very promising, but we have performed also another variant of shot peening, that is severe shot peening, in which we are multiplying the kinetic energy that is being applied to the sample. So if we imagine that this is, let's say, the pressure that we consider a fixed pressure during conventional shot peening, that would be, let's say, the higher level of pressure that we are fixing and applying for duration of exposure time during severe shot peening. With severe shot peening, we are also including nanocrystallization, and that would give an additional, let's say, beneficial effects for the mechanical performance of materials. But we are always having a problem with softness, because peening is anyway inducing mechanical, let's say, plastic deformation on the surface, and that would cause additional increase of surface softness. So we try to apply a twist mechanic of peening with gradient. So no longer the pressure constant during the process, but we are gradually increasing the pressure as we are peening the surfaces. So we define two different gradient shot peening treatments as ascending severe shot peening, so continuously increasing, and ascending descending, which is the green line here, so increasing to some point and then gradually decreasing the pressure of the impact of the media. We apply these different treatments on samples by laser powder fusion, and perform the series of experimental tests in order to characterize the effect of conventional shot peening with respect to severe and with respect to the gradient shot peening. We paired it also with heat treatment in order to check also the effect of the heat and how they would interact on the mechanical performance of the part. Here you can see the profile for micro hardness and residual stress. As we said, by shot peening in general, we are increasing, using, let's say, surface for hardening, so we have increased hardness close to the surface and gradually decreasing for all cases, and we are getting quite a deep compressive residual stress. What is interesting is that the gradient is giving us the same, more or less the same trend in hardness and also in residual stresses as severe shot peening. But the difference is coming here when we are measuring surface softness. You can see that we are starting from very high surface softness for the as-built material that is typical for laser powder bed fusion. Almost all shot peening treatments are decreasing the surface softness. But interestingly, we see that the ascending, descending severe shot peening is kind of reducing the softness. Although it is inducing a very deep field of compressive residual stresses, it is inducing surface for hardening and nanocrystallization. But at the same time, it is able, let's say, to decrease also considerably the surface softness of the parts. And the results of that would be reflected in peak performance. So we performed a fitting bending fatigue test on our samples. And as you can see, all the shot peening treatments are increasing the life of our samples. These are tests that were performed at a constant stress level for different samples of the same group. And what we have is that in this slide on the right, you can see how many times the so also with classic shot peening, we are increasing, but what we the highest increase that we are obtaining is for ascending, descending severe shot peening, both in case of the with heat treatment and without without and with heat treatment. So with especially for heat treatment, we are 50 times the fatigue life of our samples because of the combined effect of compressive residual stress, but at the same time reducing considerably also the the effect of the surface roughness. We are also performing simulate what happening during the post-doctoral training with all these different treatments. It is an ongoing research. I'm showing you just the initial results. We are starting from importing the scan surface of the additive manufactured part that is quite rough into the final software that is Abacus. In this case, we are defining a code that will replicate random points and impact of the shots as it happens really during shot pinning. And as we increase the number of the shots with a specific velocity that is replicating the element intensity and the pressure of the parameters used in the experiment, we are able to capture both the surface roughness and also the depth of the residual stresses that are obtained in our samples. These are the preliminary results that we have obtained and ascending severe shot pinning. As you can see, the comparison of the roughness parameters with respect to the experimental data are showing a very good match, and we are having also good agreement of the residual stress. So we are planning to use this numerical model in order to help us to predict how the parameters of the gradient shot pinning would affect residual stresses and roughness. To wrap up, experimental and numerical use as a post-processing treatment for laser powder bed fusion, because it's able to induce compressive residual stresses. It is also able to close small pores that are very close to the surface, so reduction also in the overall porosity. It reduces surface hardening, but at the same time, not it is able to decrease also the surface roughness, starting from the very rough surface that we have in the as-built state. And with that, I would conclude my presentation. It's the diffraction measurement. So we started, let's say, on the surface layer with the diffractometer, and then layer by layer, we removed the material with electropolishing and repeated the measurement at different depths. In the past, I think we have compared it with neutron diffraction, and the results seem to be quite accurate. Of course, when we are removing material, that would cause some relaxation in the let's say in the residual stresses, but we have applied a theoretical model that is able to, let's say, correct the results for that relaxation that is due to material removal. Yeah. The problem is that the as-built material without any treatment has really poor mechanical performance. It has a very high surface roughness. I think I can have some images also maybe from the morphology share. So it has, because you have randomly situated partially melted powders that are agglomerating in different areas and are acting as local notches. It is untreated, yeah, as built. And we have also tensile residual stresses. So there are a lot of, let's say, factors that would be affected by pollution. So thank you very much. Second presentation. That is yeah.
So So it's quite hard to use it for fragmentation tests. If you do fragmentation, expect the general it's quite common to use simple handle tools. It's more common probably than to use model only solution, case solution for plates. There is one big problem with this. This bending is to some extent provided that we have a very steep load frame, we can treat the steel, the brake instead of the steel. But a lot of load frames out there, the older, cheaper ones, made and so the case solution for this specimen is very some common solutions. And then that's not the or we have other yeah. We require that common market comparing to solutions. So the current work is indicating that the so we found the case solution for the specimen with the group one using a linear acid material. So so this is kind of a great one. And then we should try to with HMS and we have to keep what that scale Yeah. Yeah. Yeah, I mean, as I mentioned, older. We made this time, and we can have. Thank you. This first down one reference where you define the nodes. It's a line, very narrow, right? And then around the effective figures, black elements, which every one of them is black nodes. Black to
Thank you very much. Next speaker is Dr. Stein Abdullah.
Yes. Okay. Yeah. Okay. Everybody. From there, and then we if the road and by state and becoming an entire market to get people. Okay. Some of the scenarios here, what we when you do is about the definition. Now, for initial work, actually, the definition work of from the previous event, or with the previous event, developed is on the damage standard for the D3 application or the risk application. But for this one, we try to do some predict on that damage standard. And this damage standard and we replicate that using end of field and you need common equivalent and also another so what we're going to change here is on the middle segment of this function. For which the middle segment and it's a solid object, but for this work we try to get some analysis of the middle structure and we want to make it coming from the structure or footprint. So normally some of the applications they use numeral because of the language characteristic of the numeral. Why not? We want to teach many numeral. It's just everyone thing.
because of when the ability to manage other state of the like so we want to see that characteristic. And some of the characteristics that influence the performance for our strategy, size, dimension, motion control, and okay. From that, then we don't know, right? From our previous setting, sorry, from our previous setting, we did analysis, and then we what is the result in the analysis in the data. There are different probability or different technicity of the whole testing structure, and and also for the structure, and also the new one that we want to study is the default. So, but in order to make the perfect first language, not really the bottom language and the density of the so we want to see what is the vector for the for design for design. This can be one of the two and therefore always the difference of the input for design is based on the nature of the input and also the depth of the input. The dimension of the proper to gain for the dimension and also from 2.1 to 4 for the depth of the input. So the objective of the work done environment is to evaluate the depth of the input for design. Having particular reality domain. One of the input we use the AXT model, AXT analytical model, and also wider by emphasizing the analytic output and validating with the model finding. So we take the data from the final element. We take the data from the final element to study the bonding integrity between the layer and we validate it together. Okay, we can do what's up. We can do an experiment and then everything we see simulation. But for this work, we need the simulation. So we have for the analysis, the model strategy. Always we do some geometric model for the element based and software for it. And before that, we use the geometric conversion analysis. And we find out that the main side for this and we use the next side. And then the second side is human for bonding facility. We have three layers or 4 layers, but we check on the bonding characteristics because our typical design, this simple design is good or not. And then we use the first visual using analytical geometry process, the technology used in design. And then the step 4, we make the remedy for the maintenance and then for the structure using the process on the method. And then we make some analysis based on the same kind of criteria for analytical for design with the experimental finding. Okay, I jump up to the step 4 because step 3 is the process and also for the step 4, this is the way how we have okay. So we have four control parameters. Design, this of the design, and the input of the design, the input for the design is like from the level one minus also deformation can be applied finally. So the control parameter is the key value for this key value and it is the control parameter for the design. So all of these to SI and also RI. Untuk penelitian from intake while so we use the SI value. For which SI value is the sum of the multiplication of the weightage value data and then apply value. The largest value of multiplication of the criteria weightage is the non-class data. And then on the formula, the combination between SI and RI value for which we can see that the value of UI indicated one will give you the best design and which one will give you the academic number of design, but academic and lower the our design. So from this, based on the control parameters, we the T is 4.5, 17.3, 4.5, for which the vision for microattending is must be between 0 to 1. And then we can see that the out of 4 designs, the result is on the learning side. Constant for all, we see A2 design for which we can then and then so it's highly likely based on the two value. Besides this information about and the lowest value will be identified. Number 3. So from this, based on number 3, we can see that the A to B over the other element number 1 and the other one is element number 2. Okay. So the value is another result from that column, and then you can see the coefficient into and A4. And then you evaluate it in the significant inflation building. Okay, for the conclusion, I think 70% and should define is the best will be implemented the necessary for the input for design, and then the validation is based on the experiment of the 4.8, and then the first parameters will improve the based on the data. So that is the new and enhance the variability of the and improve the process in determining the best for design for center. Okay. That's all from me. Thank you.
Thank you very much. Thank you, Dr. Abdullah. Sorry, because we don't have time for the question, and we need to progress with the next. Yes.
Sure.
Yes, we want somehow the mic. So for now, it's
So, sure. So for its extent, they have temperature. Quite up by the high temperature. But there is a phenomenon. We get an increase at low temperature. There are two common low the material at high temperature. We cool the material. So this is time for and then we have to find action for structure. Another common cycle is how you use load, unload structure, which also increase fracture resistance. There are some other we have to find that element similar to the gas fracture, and I use the weak approach. And there are global approaches where no finite element is needed, but it requires a lot of customization. The purpose of this research is to create a model, a local model that does not require finite element. In our case, we do not have local pressure. A lot of substance data necessarily, but we're working with a lot of components. It's not doable to start introducing small cracks and doing this in a concept. There are three mechanisms that it's fracture blunting and it's grain hardening to plastic stone and diffraction. All of these three mechanisms depend on amount of plastic with the plastic stone. So the idea here is to use the plastic stone side. We also need a fracture criteria. It works like this. We form to the point where this cannot perform further. It then cool the material, find out the room temperature, and we get a theoretical and that's not all plastic deformation. But as the theoretical room temperature plastic stone reaches outside of the then we get active fracture. So the fracture criterion is fracture happens when room temperature plastic. So we want to find the size for the plastic stone without defining the element model, and one way of doing that is fracture mechanics and strip yield model. We have to make one modification, and that is in the classical strip yield model, materials used to be ideal plastic, but in this case we must include we need two pressure tests. One is just and then in order to use the strip yield model, we also need a K solution called K law, which is for a phase pressure. The machine model is recorded as small scale, so we need to take into account and I do this in a simple one. It's a complicated model. Just a technical consultation. We need to estimate strength in the block. So So the selection done approximately based on the circumstances. From the circumstances, from the bottom, provide that with the size of the plastic zone, we can approximate some kind of average plastic zone size, plastic zone stress strain. So this is how it works. And then I see both. This is what I mean by what's the ideal plastic. I will explain a lot of so we have control about first of all, this with respect to when we topic. First equation. What we have that's the point. That gives us a and that is definitely and it is interesting. Our share of the fund so where is it? We include pardon. Then the solve time this is the first they do the same thing now, considering raw the plastic sulfide in constant, but the pressure is unknown. But it's all in the exact same way. So let's have a look at the problem. At the back line. The top and in some cases it is better than the amounts. The two bottom figures are for the complicated prediction is someone so in conclusion, the model prediction is satisfactory, I think. And the main benefit is that you don't have but we also do not have to do computational handling simulation to many small fractions. Yeah, thank you. Well, the idea is kind of avoiding
Thank you.
The next speaker is Marco Gatti. So the title of the happening is that as conducting response of a that is started by Lana of the right.
Good afternoon. And then model the experimental behavior. So here I use it in project until now the report. So I can do some test on video. So some field element situation. One experimental test. The next step is to produce assessment. This is the outline of my presentation. It's a because of in the timeline. So now so this is the and then we order the cycling period come out to work model. After we use only money from the find our goal to find an accurate and proper way model conducting the response after the stability state computation of the manual. And then of course we propose that the so here as an example I got about here. Quite similar to the department. Okay, that's one that I could present the result of the data as one of the assessment that actually performed. So this is the experiment of staff for the department here. We now have a because we are 0.7% of strain amplitude under the and of the here the middle part. Here the experimental results if we compare the systemic response, we should be important. This one here. So basically, we have a full section of the structure in the 16 section. And for example, by the manufacturing process. So just to explain what the mean by definition of chemicals, we observe that the design the cells in the real life specimen and and then we make another connection. Before I conclude that, the general tested after based on the results decided to increase the number of seconds in the action in order to the input of the long mechanism. So the difference between the experimental and the results are made with the dimensional analysis. And then we can also some other so now we can put my presentation. It's a Charlotte. Concerning the most test of the you see that the response of human cell is representative number of cells in the section disease. And finally, the results of the across the dimensional error in the PN development model. So with that, I conclude my presentation. Thank you very much. Yes, that is the amount of doesn't cover for both the large estimate and the large estimate. The dimension of the set that we tested is 4 millimeter with the diameter of the struts 1.1 millimeter. But we are planning to produce different dimensions. So as I said, with 2 millimeter with 0.4 millimeter of the diameter. No, maybe worse.
Any other question? Yes, please.
Yes, we calculate our effectives. So we divide into the area as a calculation of the cross section of the land. Well, the effective strength is universal. Yes.
Thank you very much. Okay, so I'm going to invite the next speaker, yeah.
We try to improve when we do that by increasing the stability of the field element. And the idea, of course, is not only have to delay the total instability, which is the lattice compression, and the see from the outside compressor plan. Coming up between the common ceiling that you see on the left side and the idea that we want to use you see the velocity of the common ceiling and while the first leading the maximum depending. The idea on the parts. The idea of the we use for the area. This is how it looks like in the landscape, and we tested this specimen in physical capacity that we from that before. The loading is we presented now. On configuration in the four point ability, concentrated force based at 800 millimeters bar. The loading was applied from the loading device, the roller, and for the support, before we finish it, we also put some test for the maximum force. It is my speaking. But what we obtain are qualitative results in terms of technical the
see the yeah. You know, by looking at the chart, the reflection of the top component, you know, more than the bottom line. Here, the line. And this happens at the value which will be yellow line. Then we have the plastic which is the red line or more than which is exactly the values that you obtain, or less exactly, the application of the was observed. So this is the green line, the recognition of the two flanges, which happens at 110. So this is the plastic domain. And also, by considering the very multiply the yield limit with the modulus of the figure, the cross section, we obtain 68.1. I use the area limit of material property for the flanges, and we obtain the value of 68.1, which is the point where the plastic strains occur. You can see here that the black line, which is the behavior of the beam, does not go on the same line with the plastic rigidity of the entire beam. In conclusion, the plastic because of the very by thank you. Oh, I should go on
The next speaker is Dr. Caterina Nogara, and the title of the talk is Machine Learning Tool Applied to the Prediction and Interpretation of the Structural Behavior of Existing Data.
Good afternoon, everyone. Existing ones. Prediction of movement that really is able to measure this present two chemistries of water level and measure temperatures. Measured in here, about temperature here, consider and we can see that there is a periodic annual trend for the temperature, but also give me a rather it is here actually in water level. The second type of variables there are then we have string behavior present information in formation and also in information. And there are also programs that are able to measure the pressure after the here in the lower part of the slide, these are also study. We can see a cross-section where 19 labels the second room and the first one. I know that CP2 and CP3, which we call are considered for our discussion. Now, like, now the 7 years of this dependence and the reporting statement of CBG1 and CBG3, and then we can see that the range of statement of the point CBG2 is wider than the range of statement of CBG3 with information and this is the influence of now we see the variables and the response variables and to our data setting we need to model for the prediction. The first thing to do is calculate the model and this calculation we need to put and update data. This is the actual variables and inputs and this is one of the response. This is the target of our prediction. Which is where this is the contract that we do in the previous slide. After the calculation of the model, it is able to register new statement and model in the estimation of the environmental variable. So now we have the files and we have also to define which is the bus. So we have to define number of threshold and the lower threshold for our decision. Now we have the way we have a threshold and we have we want to focus on machine learning approaches. There are several algorithms that we try to apply to protect machine learning across the world. But now I want to present only one of the types. This is the discrimination system. This is using two different algorithms inside it. One is the relative, and the other one is process, partition process, we applied so this algorithm to our case study, and we decide the result. Our inputs are water level from the measures, the temperature, the complex measures, and also our time-related variables. Our output is the treatment in the computer group, and we divided the dataset in two parts. The training part that was from 2000 to 2009, and here we see in yellow the prediction, and in blue the measured improvement. In the training part, the values perfectly the same, while in the test part is the wide variation. In order to give the index of accuracy of the model, we can start with compute the mean absolute error. That is so our index of accuracy. Another aspect of this algorithm is that we can compute also activity index are useful for understand which are the most important because we see that water level has a higher percentage. In conclusion, we can say that this progression tree is an algorithm is in the complement. So, probably perspective size of and also not sensitive to input results. There are other algorithms, and also these other algorithms can be very accurate. It depends on the implementation, validation, and multiplication process. The next step of the researcher will be to implement an entire warning system to the safety assessment of the structure, and to that we can do the assessment for able to give reliable answers. So that's all, and I thank you for your attention.
Thank you very much, Sabrina. Do you have any questions? I would just think because you are working with data set in the next years. So how many years of data you need from training variables?
Generally, we are using areas
But did you have predictions?
we try to be part and either long-term from about 5 years. Maximum study 5 years.
Okay. And you got some over.
Yeah.
Okay. Thank you very much. Very, very much.
Here, this is the contribution of the University of Bologna, and today I'm going to talk about the case that is impact of multi-layer coding, particularly specifically with PLC, and update on the algorithm implementation. So this is my level of the presentation. Frontally, the impact on the second key engine. In particular, algorithm used in analysis and automotive thanks to the excellent mechanical properties and physical properties. But one problem is the low hardness compared to very remote. If the application was but one optimal solution is the application of our this is considered could to the application of three or more technology. Well, the content of the in particular, in this case, we included mini layer that was I think the most coding is able to application is to be compared the one the question is somebody that So we have two different conditions, content and content condition. Content condition, so we talk about how to we are right? And the market people are similar, we can conduct the observed from the this part was part of the development other the of the neighborhood. The last one
What we're doing the next speaker to show that with the title of the talk, experimental and numerical analysis of fraction interest level computing.
Good afternoon, everyone. I'm Abdullah, and today I will From the same last. Now, in order to look at and the biologic distribute over here. The display field and all part of the model and then this funny is the response shape, as you can see, it shows the point is on the articles also and while unlearning the stress, you can see that what actually it's all the after those release components, I think that and here this can see the chat components which are obtained from the and this chat component shows
Thank Thank you very much. So we have time for questions. Is there any question from the audience? So I'm just curiosity. You show in the last slide that based on the load you can estimate the current. Are you able to estimate the number of the number? But you cannot estimate, for example, if you have 3, 4, or 5 tracks based on the load.
Based on the load, how much you because this number of tracks are different for the although there are other and this is
Perfection, yeah. Estimate at the beginning, yeah. Yeah. But at the moment, with the finite element analysis, we just replicate one single track.
Yes, I will.
Yeah. Thank you. Any other question? So we can-
Good afternoon. I'm Matteo Zani from the University of Bologna, and the presentation I'm going to show you about the mechanical behavior of atmosphere manufactured via laser particle fusion, and in particular on the effect of an hybrid equipment on its tensile behavior. Briefly, full field, about what full field in particular, have an extraordinary high mechanical properties. Example, the combination of composition, treatment, but are extremely sensitive to microstructural effects. So conventionally, they are difficult to use to obtain extremely very low number of effects and negative effects. And there is interest, sorry. Is interest in the active manufacturing process of the filter
in view of the maintenance time enabled by the On the other side, active manufacturing processes, and in particular, the laser powder diffusion, carried out also needed to particular detectors that have the diffusion of the gas processes would have a negative effect on the chemical processes. Mitigate the effect of these defects, traditionally, another step is by the application of high pressure of liner can lead to material classification by several mechanisms and the closure of the defects. With the defects in the case, we intend the voltages, voids, so we don't intend the metallic on the sides. On the other hand, of the testing is very limited to zone to be played after the treatment. So the plants in temporary treatment required to obtain the desired structure properties must be performed after the heat process. However, innovative policies enable the direct transfer for the heat condition. So we can now integrate the heat and the transfer temporary treatment into a single treatment cycle that reduces the cycle time. And the objective aim of today's is that the strategy is to evaluate the impact of some kind of treatments for an integrated on-site and the treatment on the behavior of this kind of steel. Clinical costs were manufactured by IGF from the thousands of the steel with the composition of the table. And submitting carbon was still containing the chromium or the carbon carbons. Bars were then self-driven and treated according to different treatment procedures. Conventional treatment and the aggressive one. After treatment, the substitutes were manufactured in the treatment procedure, and then they were mechanically the treatment is from the same thermal alcohol, but the CST conventional treatment was performed in the pressure in gas. The dancing and movement temporary treatment with a substitute temper for the computerization of the table of the light. In the instead, the aggressive treatment was performed under higher pressure. Sample manufacture was applied during the application section. With protein became and people out of substantial after application. Compared to the conventional treatment, the duration of the step was increased from 20 to 40 minutes to promote material purification and the removal of the process effect. This aggressive treatment has a beneficial effect on the density and potential, leading to near density signals and resistant content of people vessel. Note that the vessel originated from the chemical sectors from mainly gas processes and little number of however, no resistant factor will observed on the side behavior. Factor the aggressive treatment that will improve density and hardness of the but in analysis of the organization of the reduction of the factor, so reduction of the steel. Not on the protein factor processes, but in normally conventional or the aggressive treatment, the steel exhibited the typical chemical factor of the materials, but population of molecules deviated from a single distinct unit in polyethylene and propagated the whole surface. The presentation factor calculated and discontinuity observed at the characterization appear comparable to different conditions and comparable to the factor toughness of the information produced at the part of the seal. That indication from numerically confirming that the structure of the field occurred when the secondary factor and the most output factor reached the factor toughness of the field. And the other no difference in the size of the field factor that is the stabilization factor was observed in conventionally the effective so, we different lead to the same factor mechanism and the data from the factor of the same type of explaining at the same time. However, the introduction was explained in the view of a critical student in a described the longer relation of that type factor. Because time to promote the material. Focusing on killer effects at the characterization site, we can see that the conventional factor was indicated from lack of food tolerant structure, lack of killer effects from the laser powder temperature of the process. With the particularity that the factor presented in sites, non-metallic inclusions on the surface. Non-metallic inclusions of the electromagnetic surface. On the opposite, pure effects in the samples exhibited a size and a shape similar to that of the effect, but a different surface conformity. The conformity was overlaid by impulse and signals, and they presented a narrow attached morphology resembling facts. The presence of impulse indicates that the surface of the factor did not exist prior to the contact, but was recreated during the tensile loading. Same kind of effects were observed on light structural analysis and identification. And in particular, you can see that the electric treatment resembles the shape of another effect, but with a considerable lower volume, the target field is the quantitative inclusions that we have. So it was proposed that the complete that they have the same kind of effects, not from the course. And the presence of sites site effects indicated the complete removal during the forest passage. It was confirmed and so after the treatment, stuff like that with the non-metallic sites. During the site test, early the oxide layer phase calculated the capacity to identify the shape of the original lava function, and then the factor propagated from that you could actually see the factor directly propagated from the great system lava function. And I don't think I have time the results, so thank you very much. Thank you. And so the president That's one part of the near project, but the machine was reported after the implementation, after the implementation, and the other subject. So we want to think that the answer will not closed by user. So that's the internal by the water perspective. The way internal is the but moving the
and welcome the next speaker, Ms. Andrea Larola, with the title Static and Dynamic Design Vector of Garganol Geodesic Oscillator in different year groups.
program. I'm going to your areas. Collaboration with the department in recent years, environmental and environmental research is not due to the mechanical resources. First, leading to growing interest in renewable resources in the economic sector. But in the automotive industry, it's not only a matter of green solution and but also renewable resources. In fact, European regulations are promoting green materials to lower the local costs. In fact, the majority of circular economy is petrol-based fossil industry, which represents negative impact for the environment. For this reason, carbon-based materials have to be substituted by water the most promising and ready to use technique is then to lower the carbon footprint in material production is the use of bio-based In our work, we wanted to investigate the possibility to use two commercially available bio-based toxic resins in order to obtain in particular, we wanted to mix toxin or resin with a very high bio content with catechol-based toxin. Doing that, we obtained 4 different materials with 4 different bio content. The methodology we followed is a reduction phase followed by a 3-stage process. Then a portion of the statement of the space of the treatment spaces, and then continuum and anthropology investigated the content of body and using the digital information to apply the strength data. Moreover, the differential science development tests were performed in order to assess the reliability of the different parameters of the value by these are the materials to use These are the results coming from the differential science test. And as you can see, there is no hint from representative reaction because the tests were performed on already cured cells. And as you can see, we obtained the vaccine of these lines are representative to the 2020 services for in order to let out the your content. In fact, we are different models that by increasing one value overall, we can say that there is a high recommendation of using the content, but then there is more relevant for the users. Not for the reduction of the toxic behavior, here I represented the central substance with the objective to enhance the effect of the sun. In fact, the slide we can make the models and use the content. When I reading the total content, we reduce parameters and overall, we can say that these lines are representing values of the elastic models for the field generations, and it's possible to see how different this is by using the total content. Similar to the frame rates and increase in the elastic model. The same can be said also for the lots of the field mechanism. And in fact, also here we have almost
this slide are reported the concentrated basis of the 4 different materials and the different strain rate. As you can see, by increasing the strain rate, we can see a slightly more brittle factor surface. Whereas by increasing the total content, we obtain slightly more ductile factor surface. But overall, we can say that the failure happens due to a void or defect in the material. For example, the material, 27% of total content, that's a quasi-static condition, which is here represented, can be the presence of an defect can be verified also by the system. As you can see from the video, there is a concentration of the strains in a particular zone of the iron interest. So, in conclusion, we can say by increasing the total content, we have a reduction of the GP values and a linear reduction of elastic modulus strength were found by increasing the total content, whereas an increase of modeling strength was observed by increasing strength rates. Most important from the analysis of the resin with the lowest zero content, it was possible to see that they have comparable properties with the commonly used epoxy resins. Just replacing the epoxy resin with the new base one is possible to obtain reduced environmental. In the future study, we want to investigate the behavior of these materials at different temperatures in order to evaluate their application to automotive fields. Thank you for the attention.
Thank you very much, Andrea. Any questions from the audience? Yes, please.
Yeah. So this, how do you explain this?
I said that by increasing the total bio content, the fracture surfaces result more ductile, and the same can be also seen, I think here, that increasing the percentage of the highest bio content resin, we obtain higher elevation. So, yeah, it is more relevant. Just in the first graph, in the second, and over 4 thirds of the gas. But it's very difficult to avoid the presence of the defect in the basement. Because we pour the resin with a silicone mold after the decapitating after the
Yeah, you can discuss during the coffee break. So we can progress with the next speaker.
from the
Good afternoon, everyone. I am Julian Park from Kansas University in South Korea. The title of presentation is develop global cancer testing machine for this program. I present the proposal. First, I'd like to present about the introduction. Clinical properties are important and then of the clinical structure. Thank you. Connecting devices can display for mouse space. However, the game of motion computers is different from work computers. Depending on its skills and application. So, it is important to easily obtain the properties learn theories for enable design of components. So, it's therefore, we developed new kinds of tests. Second, I would like to introduce on previous is we developed the cancer testing machine for as you can see this slide, we use the voice coil as actuator and node cell to measure load and displacement measure displacement sensor to measure the distance between grips. So we have developed a new cancer test machine for observing cancer mechanism. Cancer test. We made effort to develop the test however, we found difficulties to develop unidirectional cancer test. We cannot observe the move to one side by bidirectional. This image shows same images
for 10,000 times. Therefore, we developed new test machine to overcome problems of high load on both sides of the specimen. So, we can test the therefore, and find materials inside the such as cell one, we can see the size of the manufactured test. And also, we found that all the different if you use the node cell inside the vacuum environment, you can see in this figure the different cell strength of the vacuum. So we designed the structure spring for rendering in vacuum. It is several containers for either heat and variability and depending on spring surface. You can see the manufacturer springs various thickness. For using spring, we calibrated the spring of various thickness. We can see result in this figure depending on sequence of spring. This slide shows photos of the developed high dimensional samples. We use complex microscope to verify practical utility of bidirectional cell. So we can continuously observe the shape of material and find various benefits as you can see, then the material almost symmetrically deformed with respect to its center. And we performed the tensor test of carbon circular with a sequence of 5 micrometers. To compare with mechanical properties using unidirectional and bidirectional tensor test machine. As you can see, the results are almost same. Finally, thank you for the presentation.
So I want to invite the next speaker, Federica Buccino, in the talk titled Syndrome-Based Lacunar-Inspired Biomaterial for Mini-Invasive Bone Repair.
Sono tutte e due, vero? Ok.
So in this brief video, I would like to immerse you in novel ways to see fertility from a more human-centered approach. This is because basically when so we are talking about the people that is more linked to a more psychosocial and psychological sphere. The point is to this enormous issue we need to deal with complexity of the with a major change in the cortical aspect of the structure, you need to be minor scale with the force. What we also did, it clear but this is important to be however, to avoid we are now focusing on less even medicine strategies that focus on infectious substitutes, such as the scaffolds that are seeded with mesenchymal cells harvested from the patient itself. So we are focusing on more continuous strategies. This is the
new form. To tackle this question, we have
in Trieste that allows us to obtain with an adult design by the ceramics polymers, but we have decided to focus on the scale of people that these are natural polymers that is particularly of the material itself. So we have this so we itself. It has a limited weight and limited height to be compatible with the rotation of the in terms of the testing phase, the tests are conducted on the distance and with such a high resolution that is 1.6 microns that allow us to capture not only the morphodynamic characteristics of the structure itself that are not visible with other traditional approaches, of course, inside it. Moving to our immunohistochemical approach, we have and see whether our scaffolds that are and we have to identify how much more is flowing inside them. So we have been able to for both the presence of calcium and of collagen. Inside the construct, specifically how many mesenchymal stem cells have been differentiated inside our construct. Now, with architecture, we have the density of those constructs. We have applied some artificial intelligence-based approaches that we have computational neural network to identify the new foreign-born quantity inside. And with this, on the right,
consequently, the study of this work with this tool, we are now able to detect the of the force and the force point, and now use indicate by the 3D biophasing approach to realize things after entering the market by understanding what is the state. I would like to thank you a lot for your work.
So for sure we will have several questions during the coffee break with the presentation was done.
Okay, thank you to everybody, and my name is Morgan, and I continue the department this work is a part of the previous research project that Federica instituted. Federica described the work on treatment, and now this work focuses on a study investigation of the micromechanism of bone damage. Federica already said that the bone is a really complex material with a multi-cell divided into the macroscale, the mesoscale, and the macroscale. We will focus on microscale, where we can distinguish, for example, lacunae, where there are osteocytes, and we can decide to distinguish the final aim of the different temperature consists in elucidating the microdynamics in order to identify the effective origin of cracks and the propagation. Because we think that the microscale damage is the most important failure in order to understand the effective cause of damage. We think that this will improve the knowledge of the scale of damage. We will improve, we will obtain and more diameter and that also. This work is composed of several steps. The first step, the chemical doctors, following the human body. The samples from several analyses, waiting for the genes and you can see the samples. You can see here, this is a sample. The dimension of the sample is the sample has a square cross section. The dimension of the samples are counted following the reference direction. Belonging to three different antibodies, there is the two investigation. There are the different groups. Federica has already described the micronucleation device that we use in silicon in order to investigate cycle state. Synchrotron allows us to obtain images reference to of about 1.5 times. So we by the sound performed on synchrotron, we are able to obtain effects of a very high resolution. The experimental tensor, the chemical chemistry of the experimental tensor, the samples are put in the microcompression device, then is performed the calcium, then we apply a load, we perform another and so on. We apply the load and after this load we perform. Here you can see some examples. For example, this is the standard performed without any load adjustment. And here you can see a standard performed after the work like load. There is that was not present in the previous standard. And here you can see the effect that is propagated after the application of a more load set. So by means of this center, by means of this images, we are able to follow to investigate the effect origin and the effect propagation. If you can all the numbers that we were able to for example, the image propagation. For example, here this is interesting here some property mechanism called length bridging, and okay, here you can see the comparison. For example, in case of energy patterns, the number of property mechanisms are easily higher of so here you can see other okay, here you can see the analysis of morphological analysis of and then here you can see because there is something analysis we're able to find out that the process of improvement in case of healthy and also in particular, in case of healthy patterns, the shift of the component along the direction of the load. In case of the growth starting the shape of the lacuna in the more circular, and here is the point, I think we found out that in case of energy that probably affected the so similar in case of lacuna, we found the following, so we propagation velocity in is higher with respect to the tech propagation of the direction. But on the contrary, in case of cosmologic target, the tech propagation velocity around the is not higher than because again, you can see, okay, again, you can see this slide, you can see all the investigation we performed. Here we examined crack property displacement, and we measure the crack property displacement by means of this parameter. We were able to evaluate and calculate the strength density factor. And then here, by means of the temperature, we developed three dimensional calculus in order to determine the most stressful zone that effectively corresponds to the a zone where was where there was a here we evaluated first really first okay, so just developed the procedure how to perform the and so we were able to evaluate now we are developing several points that we need to improve. First of all, you students understand that this analysis of our GI and analysis, you can, for example, that to provide the kind of sector of the data correspond about one type of data. So now we need to we have improved, we have developing this model for the automatic effect and data. Then we need to validate more samples for validate the model and in order to correlate the
So I want to introduce the next speaker, Professor Motto, that will present his research titled Exact Solution of the Equal Space Dislocation Rule concerning infinite plate and its application to hyperspectral analysis of related problems. The floor is yours.
I will keep the time, don't worry.
Yes, thank you. My name is the J using many methods. For example, is as you know, I will training method. The M is a more popular method in that way. The E now to give the of the tool is a field. Only a because the method role was a field. However, we can expect that the appearance is a country solution by Professor in particular, the method of Therefore, the first step of the traffic analysis by the function of this function is defined by this equation. Now, I think similarly, another example. The next
Depends on application. The first example is and this is periodic drugs in our research. These drugs is different is a continuous related to deportation. And these drugs is substituted to the same condition. So the deportation that we reach drugs and so and so the and the front of the function of the service is described as a serial interpretation. And where the common function is location density and the integral object can be described by using a calculation of equal space of the function against the assembly. And by something that's like big and big, it's on this, and this information can be so unique and based on then this is the result. And only for the swing of the number. And N is the number of the rotation points. The convergence is very fast, very good. And next is the periodic age graph in the by n scale and all the calculated results are printed and printed on by O. And the next one we have what is the point inside by the data by the final example is expression the and no time around what is that. So in case of it is important
Thank you, Professor, for the introduction. So first of all, I'd like to show you the general context very quickly in which my research activity is inserted. So the additive manufacturing, in particular the food filament fabrication of plastic material, is becoming a very important production part for the industry, and sometimes it also replicating from production approaches. As a benefits of this. On the other, it increases the this is high so then actually parts use technology to answer the industry. Obviously, first of all, we started traffic and performance of the treatment materials derived from the optical set. Okay, but on the other, we have also supported the desire to predict the load capacity of the technology of the components. So, for example, using these elements, the goal is find a simple and robust way to predict the center of your components. So first of all, the method that we use the average strain analysis density for the first and the first beta in the last statement agreement. It means that we probably we can we have to know the notch geometry and in this particular activity we are advanced the shape and notch. And we also have to use some hypothesis of the express case. In this case, we use a end train. So the function of the average density is part of this equation, and the function only of the radius of the critical area and the other only material. So in the and fitting element. Of course, the goal of we fabricated the statement, of course, the standard of one statement for sensitive or the depending not less from 0.5 turns to 4 millimeters and the statement process. All the statements are produced in the horizontal configuration following the printed parameters that are put on the right part of the slide. Well, we can evaluate now the PRA and the characteristics and identity. We do that using a very simple sensing test. Of course, we have also to validate the manufacturing process because the additive manufacturing technology can influence these parameters. And to do that, we use an extractive process. So we use only a set of notch statements and we perform a sensing test. We record the experimental parts and we will get that identified simulation. Variating the radius where we evaluate the physical energy density, we can arrive to this energy equality. Some of the radius that verified equality is the radius with which in the inverse formulation we evaluated the package. So now we have all the, but using only the standard criteria, we have a, so I would like the results only on that not be reduced part the theoretical part decrease. So we have a no confidence trend that obviously is also confirmed then with the experimental results that show a trending trend physical. So what are the limitations of the experimental identity? First of all, the fact that we have a familiar for objects and use technical or linear model without some contribution. But in the other hand, we have also we use and also it takes a lot on energy contribution. So the thing is to evaluate the equivalent material components. So using that is possible to overcome all of these problems. So in our flowchart, we have to have the equivalent material formulation, and with this we have to recalculate all the parameters and the fracture factor. At the end, we have in this way a correct trend of the force. And if we report in this slide all the results for all the events, we will see that the power is in the 20%, and also in the formation from the statement that right. So again, you can after that we can find that useful for the value of the DNA region. Thank you.
So we can go towards the end of this session. So I'm very happy to announce that we present an interesting research titled Sculpture and Fracture Mechanics.
We are scheduled, we like to move. This is probably the university in Spain, but one more comment. The oldest in Europe is Polonia. Is to go forward away. But we look to the cluster. The cluster is the motivation relationship with science. Very normal. In a conventional machine. Anything, you know, structural material. Then I will in the most heavy of the skin, the reflection of the light is the whole picture. Be connected to this one. In the not form, imagine I think it's the limits of whole rocket. Un Michelangelo. Un Michelangelo. In el Museo de Arte Michelangelo in Milano, los conoces. Cuore, no? Yes. Venice,
You know, the chairman is Professor Titano, but so what is the so I want the section for a second. So we check your presentation 1 second if it is working. Yeah. Yeah. Perfect. Thank you. Yeah. Prego, prego. Posso chiederti se c'è qualcun altro? Aiuto, no, where is the PowerPoint? Is it one? Okay, perfect. Okay, good. But then I'm not the chairman of the next, but in any case, we can check if everything is going well. Yes, I think it's fine, perfect. Okay, the next 1 second that I. Thank you. Magaro. Yes. Working. 1 second. Thank you. Quella di Roma. Ah, bene, dai, ottimo, fa un piacere conoscerti. Quindi, no. Sì, funziona tutto, perfetto. Ottimo, adesso magari ci salutiamo fuori perché questa freccia e dopo ci sarà il puntatore, diciamo, quello di PowerPoint. Okay, 1 second. Giacomo Risitano, cioè no. 1 second that I check. Sì, ma dovrebbe esserci la studentessa di Jacobiello. Is this one? No. What is, okay. Second, we check. Yes. Okay, so we are ready. Adesso in caso gli dico di andare da Quasi.
Ah, okay. I don't have one. Yeah.
Volete caricare il nostro?
Sì. Sì. Un secondo. Grazie. Queste sono state carine. No, voi non lo sapete, ovviamente. Questa dovrebbe essere la sessione 4, la vostra, vero?
Sì.
Ah, ok, perfetto. Allora sono già. Tutte e due?
Sì.
Ok, perfetto, grazie. Il video? Ah, ok. Questo? Ok. Le taglio direttamente perché questa tanto non servono più sulla mia pennetta, penso. Vabbè, lasciamocele, magari abbiamo difficoltà. Grazie a lei. Which one? IGF. This one?
Okay.
Good afternoon. We can start. Because I
Yeah. Yes, I'm myself. If I speak from yeah, I'm gonna be loud. Okay. Okay, thank you so much. I am very glad to present you my work about the assessment of the fracture of U-notch and V-notch specimen made of aluminum lithium, third generation alloy. I would like to acknowledge the support of King Fahd University and the Center for Interdisciplinary, the Interdisciplinary Center for Advanced Material in KFUBM. This is my outline. I will talk about the alloy, and then I will strain energy which were used to estimate the fracture. Then I will just talk about the experiment and the result. Okay. Okay. So the main objective is to investigate the U-notch specimen fracture for aluminum lithium third generation alloy. So this is a third generation aluminum lithium alloy. Particularly the one that we are investigating was actually manufactured by us in 2010, so it's a pretty much a new alloy. And you know that aluminum alloy, especially aluminum lithium alloy, very interesting material for. So what we are going to do is that we are going to use the strain energy as well as the area of critical. My assumption is that all of you are familiar with the strain energy density, but just in case if there is I'm going to go over it quickly. So the strain energy density basically predicts the fracture by quantifying the energy which is enclosed by that little area. So the thing then is all about knowing where and how this area forms in finite limit analysis. That radius over there, which is called the critical radius, and from the equation here, you can see that the theory suggests that this radius is a material property. So, but more often than usual, then we don't have, for example, the fracture toughness of the material, which is part of the over here. So what do? We calculate the strain energy, the ultimate strength, modulus of elasticity using this equation. And then by changing the radius over here, just repeat it to the software, we calculate the energy within the enclosed region until we reach the intersection. And by that, we will know what is RC. And once we know RC, we can. So on the other side, we have the theory of a critical distance, which is based on stress, not energy. So for the theory of a critical distance, there are 4 methods, which are called the point method, the area method, the line method. We use the very simple line point method. In the point method, what do? We use 2 notches, one which is supposed to be blunted and one which is very sharp. In our case, we machined 1 V notch specimen, which is supposed to be very sharp, and 1 U notch with a radius 6 millimeter. And then by running this and calculating the stress from the notch tip all the way to the depth of the sample, we will see that one sample, the stress variation with the distance from the notch tip will always meet at one single point. This single point is basically used to define the critical distance, which is basically L/2 and the inherent strength. So all what we need to do is to run any analysis using finite element and then measuring the stress exactly at this distance. So once we determine this distance, we use it as a reference point for all other geometries, all other notches. And by calculating the stress at this distance, we compare it with the inherent strength for other samples. And this is basically how the theory predicts failure. So of course, the theory of a critical distance claims that the critical distance is actually material. And if you see here, theoretically, it is KIC over sigma 0, which is the ultimate strength in brittle material, squared divided by 1/pi. But since we are testing a material, not brittle, then we use this method to predict or to determine the inherent strength and the critical distance. So basically we need the ultimate strength, and this is where we have a standard tensile specimen, and then this is the geometry for the U-notch specimen. All of them have the same net cross-section, which is meter in diameter, but the rho, which is the radius, is different. This is the composition of the alloy. And these are just the geometries of the sample. Different radii. We focused only on U notch. We are counting V notch, angled notch, as well as multi-axial loading critique as well for the same material. So basically, we did all the standard. All tests were performed at standard laboratory condition and with a strain rate of 2 millimeter per minute. This is the stress strain curve of the material, along with the material property. And in here, we have the fracture load for the samples at different U notches. So these are the U notch radii, and this is 2 duplicate, and this is the average fracture load. As I said, we use linear elastic for both of a critical distance. So basically, we have a quarter specimen with an axisymmetric boundary condition and a symmetric boundary condition at the bottom, and we just apply a negative pressure. This is just to show you how we obtained the critical distance using finite element for a U notch with a radius of 6 millimeter and a V notch of an angle 35 and a notch radius of 0.4 millimeter. What we got is that the radius of the critical volume for the material is 1.39 millimeter. This is the critical energy, and this is the critical radius, the critical distance, sorry, and as well as the inherent strength. This is just to show you the finite element analysis for the mesh as well as the stress field. This is the stress in Y direction. So the stresses are not real, linear elastic analysis. Just remember that we calculate the stress far away from this, a little bit somewhere in here. So before I end the talk, this is just the result. This is the result for the strain energy density. As you see, interestingly, the two methods with their simplicity and they predict the fracture really nicely, especially the strain energy density. And this is the prediction with the theory of a critical distance. So in summary, both the strain energy density and the theory of a critical distance with the point method were used for the 10th generation of aluminum lithium 209 T83. Both results from the two theories were acceptable, actually within a good range, but the theory of the strain energy density was much better with a tighter percentage of error. That's it. Thank you so much for listening. Welcome. Yeah. Yeah. I think the argument is about the fact that at the node step there is too much distortion, and this is why it's been even suggested in downward torque and your standard textbook material. Yeah. Yeah. To be honest, with the plastic material, because I'm using the material as the same theory with polycarbonate. When you see the strip forming, you can make sense that there is a theory of a critical distance with an area method or a line method, because there is an actual gradient, which is like a line. But for metal, a point, maybe not. Okay, well. Thank you.
Monitor because we have the big.
Okay. Yes, okay. Thank you. And I would like to tell you about free vibration of a conical shell with arbitrary boundary conditions using Syrian solution. My co-authors are Dubik Yaroslav and Krishuk Mykola. My name is Alexei Ishin. So why is our study important? Study of the structure's dynamics is confirmed by the recent events in Turkish Syria, where a large number of casualties were due to the destruction of buildings that could not withstand the earthquake. This is plan of presentation. Here you see dynamic, physical, and geometrical equations of the conical shell and direction of the generalized force and moments you can see on this slide. To obtain a system of 8 partial differential equations, we used a simple algebraic transformations. For further calculation, we have to obtain the explicit expression for n phi, m phi, mx phi, and q phi. We did not show the unknown q phi on the slide because of its large size. To obtain a system of ordinary differential equations from partial differential equations, we use trigonometric series expansion of main variables. Thus, the system of 8 ordinary differential equations in terms of main variables. The simplest way to find natural frequency is to define system shell determinant. In this case, the value of the roots of desired parameter, frequency as in our case, when the determinant is crossing the zero line. However, using an iterative solver in real structures, for example, with elastic boundary conditions, as an example for spring in wagons or vibration dampers for buildings, there is a risk, that the solver will miss some frequencies. The created by Wittig-Williams algorithm is a simple counter because it finds the number of frequencies in interval. The Williams-Wittig algorithm or dynamic stiffness matrix method find exact number of natural frequencies for beams or skeleton structures on interval. The number of natural frequencies, J, below omega t at trial value of omega is given by these equations. If we consider beam element, counter can be easily obtained as analytical expressions are well known. But in shell, we used only counter. Here is transfer and dynamic stiffness matrix of shell. Due to algebraic transformations, the blocks of the transfer matrix are written. Thus, we've obtained the global matrix of dynamic stiffnesses and matrix of boundary conditions with spring stiffnesses K. Such system can be solved by normal polynomials, and we can use only polynomials of third degree in our expansion. It will be as a reliable accuracy. Using transfer matrix method, we can solve equations for cylinder and create a conical shell as a set of a cylindrical shell with decreasing and increasing radius. And the second case is studied for a cone whose equations were shown in the previous slide. Dividing the shell into equal parts, for each of which the matrix with dimension 8 by 8 will be recorded. It is necessary to determine the optimal number of divisions. The figure shows the influence of number sections breakdown on the frequency parameter when using polynomials of the second and third degrees in the solution. It can be seen from the graphs that the polynomial of the third degree converges with a smaller number of partition sections. Analyzing both graphs,
we conclude that even when dividing the shell into 100 equal parts, we get a convergent solution. To solve any vibration problem, we have to add boundary conditions. They can be proposed by one of 16 types on each of the shell edge. On the left side, you see the most common one is a simple support, clamped edge, and free edge. And we can use in our solution elastic boundary conditions. Here, values K represent the spring stiffness in different directions. Comparing the results with experimental data for a conical shell with clamped large radius in the first figure and a clamped small radius in the other graph, we can see good convergence for a shell with a small radius clamped and a free large radius. Also add mode shapes for a cone at the right side on the slide. We can also compare in table frequencies obtained by formulas by cone and formulas by cylinder as number of cylinders. And here also you see literature data and experimental data. It can be seen that the results for simple cone show better convergence than cone represented as set of cylinders. The figure shows the calculated frequencies in circumferential wave number for 4 cone model with different angle. And it may be concluded that frequency of the shell with a small angle has much larger convergence with the experimental data than the one with a bigger angle. As it was shown last time for a cylindrical shell, for a real construction, it is necessary to take into account the initial stresses. Such stresses may come from axial force, internal or external pressure, centripetal force, and torque moment. To include this in solution, we used a simple relation where F is initial force, U is the displacement, and these components are included in the matrix L. To compare effect of initial stresses in conical shell, experiment by Tani was chosen. He investigated the shell under compressive axial force markers on the first figure. Our solution, a solid line, compare with dashed line is an ANSYS solution for 9,400 surface element. Other 3 graphs show our ANSYS solution for external pressure, internal pressure, and external pressure with compressive force. Good convergence can be seen even at high frequency. To conclude, we obtained the formulas for conical shell without simplification at the stage of problem setting and compare them with experimental and other research calculations using different boundary conditions and loadings. Here you see contact information of our company. Thank you. Yeah. Here, you see in article this experimental test, and we want to compare this shell, this geometrical radius distance of the shell. Yes, we see on the experiments, and we compare with our solution. What? Yes. Thank you.
Thank you very much.
Thank you.
Bye.
Okay.
Good afternoon, everyone, and thank you for attending this presentation. I would like to open this presentation with the aim of the work. We know that for simple geometry and simple kind of load, it's easy to calculate the fatigue crack growth because we can apply the calculation of the stress intensity factor. But what happens if the geometry is complex, or if we have more complex loads, for example, bending or multi-axial loads or multiple cracks, for example? Well, the aim of this work is to develop a method based on an energetic approach to calculate the crack growth shape, even in presence of multiple cracks or multi-axial loads. Let's start with the hypothesis for this kind of energetic approach. First of all, the initial crack is elliptical, and during the crack growth, the shape have to remain elliptical. It means that only the semi-axis A and B of the ellipse can change, but maintaining the same shape of the elliptical crack. The second one is the minimization of the crack and of the elastic energy, because the crack propagation is driven by this minimization of the elastic strain energy. Another one is that we consider the elastic strain energy calculated for steady states at equilibrium states. Let's go to the methodologies. Imagining an initial crack having an elliptical shape, we can increment the area with a delta area, and imposing this delta area, we have different crack shapes, considering the elliptical crack growth. The crack shape 1, 2, 3, and 4 are 4 different crack shapes with the same delta area imposed by the method. As I have said, that we have 2 hypotheses. The first is that at equilibrium, the potential energy is equal to zero because we consider only the steady states. If we consider the steady states, the potential energy is equal to 0, so we can consider only the elastic strain energy because it's equal to the work done by the external forces. The second is that the shape have to remain elliptical. So imposing the delta area, all the different shapes are always elliptical, and we can perform different finite elements simulations on the elliptical cracks. At the end, calculating the elastic strain energy for all the configurations, we look for the minimum elastic strain energy variation corresponding to the new crack configuration. These methodologies can be automated in 2 simple scripts, not simple, but in the slides we can resume the simple scripts, linking the MATLAB script and the ANSYS APDL script. The first gives in output the configurations of the initial elliptical crack and all the configurations for the virtual crack propagation. This output is the input for the APDL script that performs all the simulation, finite element simulation, for calculating the elastic strain energies for all the simulations. This output of the APDL script is the input for the MATLAB script that find the minimum elastic strain energy and gives another new configuration for the second step of the analysis. This approach was applied to four different cases. The first 2 to an infinite body with penny shape and the elliptical shape. On the right, we can see the details for the mesh, and on the left, on the bottom left, the geometry that is represented, that is considered in symmetrical way, considering the highlighted in red symmetric plane for the constraints. The same simulation for the infinite body with elliptical crack, but in this case, the only thing that changed is the elliptical shape of the initial crack. The first results for the infinite body are in agreement with the literature. Imagining the infinite body and the penny shape, we have an initial crack that is circular. And if we look on the picture on the left, we can see the stress state on the semi-axis that are equal. If the stress state is equal, the crack shape continue to grow in a circular way. And this is in agreement with the literature. On the other hand, the infinite body with the elliptical shape has the stress state on the semi-axis B that is this is higher than the stress state at semi-axis A. So for this reason, the initial crack that is elliptical starts to grow, increasing the length of the semi-axis B. When the semi-axis B reach the semi-axis A and becomes circular, the crack shapes continue to propagate in a circular way. Another example is the surface crack plate with bending load. In this case, the considerations are the same, but the kind of load is different because it is a bending. When we apply the bending on a surface crack plate, what happens is that the stress state on the semi-axis A is higher than the semi-axis B. So initially the crack starts to propagate along the semi-axis A, but during the propagation, the stress states starts to become higher on the semi-axis B. And in this way, even the semi-axis B starts to propagate together the semi-axis A. The last application is the cruciform flat plate under biaxial loading. On the left, we can see the cruciform plate that was considered as a 1/4 of the plate to reduce the model. On the center, the initial defect size, the semi-axis A equal to 10 millimeters and the semi-axis B equal to 2 millimeters. Two different kind of load were considered, one with the same pressure on the two sides and one with the pressure on the side one equal to 200 megapascal and the other side 100 megapascal. The results are really close to the beach marks represented in this picture. This is the picture of the specimen cut on the plane of the crack, where we can see the beach marks, and the method can predict the shape of the elliptical crack during the crack really close to the reality. This is the specimen 1 and this is the specimen 2. We can imagine that for both cases the principal contribution of the crack growth is due to the pressure along the direction that is orthogonal, perpendicular to the crack growth. In conclusion, this method is based on the calculation of the elastic energy, and it was applied to uniaxial and biaxial cases. In both the cases, the method gives good results and really close to the reality and really in agreement with the literature. What we want to underline is that with this method, we can avoid to calculate the stress intensity factor. So if we want to have a rough mesh, it is possible, and we can decide to avoid to have a very detailed mesh at the crack tip. It's not important if the mesh at the crack tip is really mapped and refined, because we don't have any interest in calculate the stress intensity factor. For this reason, this method is really useful to study more complex geometry and loads combination. And we can consider even the multiple cracks presence, because it is based only on the calculation of elastic strain energy and only on the shape that the crack assumed during the crack propagation. At the end, with this method, we can apply the crack growth rules used for simple geometries at more complex geometry, only considering the elastic strain energy. Thank you for your attention. If you have some question, please ask me. Yes, of course. If can I add something? This is a very refined mesh, but if we want to reduce the refinement of the mesh, it's possible, and it's not. It's possible to avoid to have this circular form at the crack tip, because it's not important to calculate the stress intensity factor in this case, but only the elastic strain energy. In this case, we want to compare the two methods, the stress intensity factor method and the elastic strain energy method. So it was useful to have a mapped mesh, starting initially a mapped mesh to perform both the simulation. Yes. Thank you. Thank you.
Thank you. Yeah. So thank you for attending this presentation. My name is Teresa Morgado, and I will present this study of extend and generate finite elements method into the 3D applied to single edge notch bending test. So I will present the framework and objectives, then the introductions. I present the methodology used in 2D and 3D simulation studies, the results and the conclusions at the end. So the material that we will use in this simulation will be the semi-specification of the railways components that are the STM A148-1960 is a steel. The principal objectives of this work is to conduct a convergent study to determine the best methodology to evaluate the stress intensity factor and the J integral solution. So here we can see the test rig, the experimental layout, and then we can observe also the geometry of the test of the specimen. So for the 2D simulation, numerical simulation, we make 6 studies. The 3 first studies was with the conventional method. To the conventional method, we start to define the crack length, define the element type, the influence of the mesh refining, the validation of the model without contacts, and define the methodology to use the fatigue study. Then in the 4th study, we use the extend finite elements method, and the objective was to study the influence of the mesh refining in the crack propagation. In the 5th study, we use the conventional method with the fatigue to define the values of the stress intensity factor range and compare it to them with the experimental ones. For the 6th method, we use the extend finite elements method with fatigue, and we validate the method with the crack propagation and compares the crack length obtained in simulation with the crack length obtained by analytic method. So for the first study, we aboard 5 length crack lengths. We start with 1.5 and we finish with the length of the 10 millimeters. The element study was two kinds, that it's allowed for ABAP Sky program. And here we present the element type of CPS4 and the number of the elements and the number of nodes.
we can observe in this picture a title of an example, the mesh for the different crack length. So we here in this in figure 5, we can observe the stress intensity factor versus numerical versus the experimental one and the crack length. So we can observe that the first order elements present better results, and the crack length of 10 millimeters was the best results too. For the second study, we studied 8 kinds of meshes for the 10 millimeter crack. So we can see in figure 6 and figure 7 the difference between the crack mesh. So the elements from test 1 to test 8 increase, and the number of nodules too. And we can see the error between the stress intensity factor obtained by numerical simulation and by experimental simulation. So the mesh refiner did not significantly influence the stress intensity factor results. All the tests present an acceptable error, less than 1%, and difference between the errors of test 1 and test 8 was about 0.4%, which shows the impact between the less and the most refined mesh. So then we study the model without contact. We apply a force and apply the restriction in the model. So we can observe for the table 2 and for the table 3 the comparison of the J integrated values and the stress intensity factor values for the model with contact for the mesh 2 and without contact. And we can conclude for the observation that the software can simulate the experimental model without contact with very satisfactory results. The model without contact presents a J integral error less than 8.2% and the stress intensity factor error less than 4.2%. The model without contacts offers the advantage of faster modeling in the test, thus avoiding solving numerical problems arising from the contact established between the rigid and the firm bodies. So, with the fourth study for 2D case, with the extent finite element method, we also study for mesh, and we established the crack length the 2 millimeters for this study. So for this study, you can observe the refining of the mesh did not influence the crack propagation results also, and the damage criteria is the most critical parameter in the crack propagation results. We use the damage criteria of stress, visible stress. So in the fifth study with the conventional method with the fatigue, we defined the stress intensity factor range and compare with the experimental ones that we can see in the table 6. And we can see that we obtain the values similar to the experimental ones in the element 8 and in the element 1163. For the simulation, we use the same parameters that we use in the experimental test. So in six
study, we use the extend finite elements with fatigue, and we validate method with the fatigue crack propagation. So for that, we study based in the experimental testing. We have the reliability for 5, 10, 15, 19, and 95% for a crack propagation of 5 millimeters. And we analyze and we calculate the number of cycles. So for this testing, we stabilize the 1,000 cycles, and the measure the damage criteria of 217 megapascal for the simulation. So with these criteria, with these values, we observed that final crack length was about 5.092 millimeters, so very similar to the experimental one. Now 3D simulation, numerical simulation, I'm running. So start to study the first study with the conventional method, and we determine the objective was to determine the influence of the refining of the results of time and compare it to the results with 2D. So we make 3 meshes, and we conclude that the 10 contours present better established results, and the nodes 1 and 9 presents better results. Here we can see to see the, I don't think it's running. Maybe not. Oh, sorry. I tried. Yes, it's right. So this is a 3D bending test with conventional method where we can see the propagation field. From the results, the contour 1 results of the mesh 2 and 3 presents an error approximately of 0%. The refining of the mesh did not significantly influence the results, and the 2D results presents better results for conventional method. I'm finished. So from the second case of 3D bending test, we use the extend finite elements method. We use the crackling of 10 millimeters. We make the numerical simulation for 5 groups of contours, 5, 10, 15, 20, and 13, and we calculate the stress intensity factor and drop the interval values. So from this case, we can observe that the contour 1 cannot be despised. All the curves are 2 discontinuities. When the number of contour grows, the relation between the stress intensity factor numerical and experimental also grows. And the group of 13 contours present results in more stabilities. So these are the generic conclusions that come from the results. And the biggest conclusions are the results show that both methods proved to be adequate for evaluation of stress intensity factor and the J integral. Extend finite elements method proves better results than conventional method. And we are acknowledged to the Fundação para a Ciência e Tecnologia. And thank you for your attention. And here are the authors. Sorry. Okay.
So, hello everyone, good afternoon. I am Venanzio Gianello from University of Salerno. I'm an assistant researcher. And today I'm going to talk about our simulation we did to simulate the welding process for butt welded joint. So we simulated the process explicitly, and we compared our results in terms of temperature with the experimental data that were already available in literature. So the motivation behind this work is quite simple to be explained, because the welding process is something that is widely used, perhaps is the most widely used methodology to join two metal pieces. And it has some issues such as it can create cracks, porosities, flex of fusion, distortion, and so on. So we wanted to simulate the welding process because at the University of Salerno, we are interested in working with small uniaxial dog bone shaped specimens with a welding line in the middle. So we wanted to calculate the residual stresses, and then those residual stresses were used, then we need to use them for a life assessment. So we ended up with this procedure that allows us to simulate the process, and then it is based on the finite element method. So this is an example of what we did in the past for a T-joint. So we simulated explicitly the welding line at two lines of the vertical, at two sides of the vertical piece, and we obtained the distortions that we compared with experimental observations, and we obtained a reasonable agreement. So theoretically, we need to simulate the process. We need to simulate this process because we want to acquire more information. In our case, we want to acquire the residual fields in terms of temperatures, in terms of, stresses and distortions to be used subsequently. So in the case I'm showing you now, we simulated the butt welded joint we see in this slide. So it is a butt welded joint of two plates that was experimental test was manufacturing was available in literature. These are the details of the big groove. So in particular, I want to highlight the thermocouple position to acquire the temperature during the welding. The material is a low carbon steel. There was a mistake in the title. It's a low carbon steel for both plates, and in particular, the welding process was in two passes, in two consecutive passes. So there's the first pass as an intermediate pass, as an intermediate joining part, the joining process, and then there's the second pass on top of the first. So our modeling procedure consists of a finite element method. This is one plate. We modeled just one part, half of the joint, thanks to the symmetry. This is a detail of the local mesh. In particular, I want to highlight the first and second pass. So the elements, the groups of elements representative of the first pass are highlighted in green. And then there are the groups of elements activated subsequently to simulate the second pass that are highlighted in red. The welding direction was the same for both passes. And we adopted the birth and death technique so to model the process. In particular, this technique allows to explicit modeling the weld bead formation during time. We're going to see a video about that. And groups of elements highlighted in blue are sequentially activated during the according to the manufacturing details. And in particular, we are going to see now we are looking at three groups of elements referring to the first pass. So it is a sequence of increments, step by step. It's an incremental procedure that starts with the first group of elements and reaches the end of the second pass to achieve the whole welding. So our FEM simulation comprises the first step, the first macro part that represents the welding, the simulation of the first pass. Then there is an interpass of 2 minutes that represent a cooling down of the joint. Then there is the second pass, and then there is more or less 11 minutes of cooling down at down to room temperature that has been simulated in a fourth macro part. Although we are not interested into now, there's also a growing contact that simulates the mutual interaction between the plates that grows in size during the simulation. This is an explanation of how a single increment works. So we are going to see now some contour plots. Those are only temperatures, in particular referring to a general increment n. We start the increment by adding another group of elements. Then we redistribute the temperatures on this newly generated mesh. Then we let the welding torch advances, so the heat flux advances to the new group of elements, and then we achieve, let's say, a final temperature field representative of the end of the increment n+1. So going on with the procedure, we incrementally can simulate the process, and in 77 increments, we simulated the first pass. Then we wait 2 minutes to simulate the interpass, so the time between the two passes, and then the simulation of the second pass, and then the cooling down. Hopefully, this is a video that should work. Okay, so this is the simulation of the first pass. As we can see, the joining of the process is sequentially generated. Yeah. Then there is the fading, let's say, of the temperature, the cooling down. Then the weld bead is completed in the second pass. And then there is the final cooling down of the joint down to more or less room temperature. Actually, we modeled just one of the plates. Now we mirrored the plates so to be more to explain better what we modeled. So from a qualitative point of view, we can see that the welding process can be simulated. From a quantitative point of view, we compared the experimental temperatures acquired by thermocouples with our numerical outcomes. So this is our at the top left corner of the slide. There is the reference, let's say the literature figure. At the bottom left corner, there is an example of what can be measured, or what is generally measured with thermocouples. So we can see the first peak of temperature is more or less representative of the half of the first pass. Then there is the cooling down, and then there is the second peak that more or less represents the half of the second pass. If we go if we compare the temperatures calculated numerically and those experimentally available, we can see that there's a good agreement between the two curves, between the three curves. Red and blue line represents the curves of the temperatures for both sides of the joint measured experimentally. We can see that the agreement is satisfactory, even though we have to admit that there is a certain scatter given by the assistant, the experimental measurements. So assistance, we can see for the first peak that there's a distance between the two curves of about, let's say, 100 degrees Celsius. So our numerical results rely on the blue curve for the first peak and the red curve for the second peak. So it is a satisfactory correlation. Going more far from the weld bead, we can see that the agreement improves in terms of both the two experimental data, and also between both experimental and numerical results. The same holds true also for the final sensor, for the sensor the most far sensor from the weld bead. So In conclusion, we can say that the welding process can be actually simulated explicitly with the finite element method. Multi-pass welding can be simulated, even though it has to be said that adding many passes increases a lot the pre-processing time for creating all the sequence, for creating the groups of elements to be activated step by step. So it is not trivial, let's say. So far, there is a good agreement between our numerical results and those experimental available in literature. And more importantly, we can say that a mechanical simulation that uses the so-obtained temperature field as inputs allows us to calculate the residual stresses and residual distortions that are the aim of our activity. So that's all. I'd like to thank you for your time, and please, if you have any questions. The software, Abacus. Yeah. We can use the same. We intend to use the same model. We just switch the type of element, and then we want to apply those. We want to use those temperature fields, transient temperature field, in such a way to calculate the distortions and stresses. So it is an uncoupled thermal mechanical analysis in which we get the temperature field and we calculate the displacements. Not yet for this specific joint. We did it in the past for the first T joint I've shown in the second slide.
Yes. Ah, sì, è meglio. Sì, sì, non ti preoccupare, sarò molto breve. Ok, perfetto. Senti, per attivare il cursore, perché non si può, non fa niente. No, non fa niente, non fa niente. No, non ti preoccupare. Okay, good evening. So this work, so my name is Daniela Pilone. This work concerns the study of copper, chromium, zirconium alloys produced by additive manufacturing. And in particular, it concerns the improvement of mechanical properties by heat treatment. So this work implies a collaboration among different universities and the National Institute for Nuclear Physics. So why copper, chromium, zirconium alloys are interesting? Because those are one of the most successful copper alloys. Due to its mechanical strength, thermal conductivity that, as you can see, is quite close to the one of pure copper, and high electrical conductivity and good corrosion resistance. In our experimental test, the specimen have been produced in the Gran Sasso laboratories by using the instrument you can see on the slide. The big problem related to the production of those alloys is that they are characterized by a high reflectivity and a high thermal conductivity. So those two characteristics can lead to the formation of defects like lack of fusion or cavities. So the powders we use for the experiments have the composition you can see in the slide. So this is the nominal composition of the alloy. The size of the powders is between 15 and 45 micrometers. So the process used is the selective laser melting process. So the process was optimized and the best process parameters were identified to give a volumetric energy density of about 260 joule per cubic millimeters. So you can see the different process parameters. We use as inert gas nitrogen. So here you can see the SEM images of the powders used for producing the specimens. So you can see that the size, the spherical shape, but you can see also that there are several satellites that unfortunately can produce the formation of defects like cavities. Here you can see the EDS analysis of the powders. So our powders contain about 1% of chromium and 0.1% of zirconium, necessary for obtaining hardening by aging. So in this slide, you see the different specimens produced for the research. Specimen that will be produced for tensile and compression tests. And so they were designed during the ASTM standards and the requirements for the Optison bar used for dynamic tests. Initially, the heat treatment was the conventional one, so the one suggested by the manufacturer of the powder. So 580 degrees centigrade for 5 hours, 9% atmosphere. Once the alloys were produced, we characterized the material we obtained. So in those pictures, I highlighted the presence of, unfortunately, of defects like cavities. So you can see on the left cavities with frozen droplets inside the cavities, and you can see after etching with ferric chloride, of the alloy, characterized by elongated grains and sub-grains in the direction where the heat moved. We performed an analysis of the specimens, and we noticed that, as you can see, chromium concentration is about 60% of the initial concentration, and zirconium is below the detectability limit of the instrument. So that means that during the production process, we unfortunately have evaporated part of the alloying elements. This is critical because during the production process, we can have a change in composition, change in the mechanical properties of the alloy. As a comparison, I would like to show you as an example the microstructure of a copper chromium zirconium alloy produced by traditional techniques. So you can see on the left coarse grains, many twins, and on the right optical micrograph, you can see small gray phases due to precipitation of chromium and zirconium rich phases. In fact, if we have a quick look at the phase diagram, we can see that both chromium and zirconium are not soluble. So, if we go back, in the traditional production process, we have formation of secondary phases. Those phases are not detected in the additive manufactured materials because the cooling rates are very fast. So we are in a very different situation, and we try to age both the as-built specimen and the annealed specimen specimen. As you can see, by treating the SB specimen, we can obtain quite high values of the micro hardness. We are around 160 beakers. And that after long time, they tend to reach the same value. X-ray diffraction show that after building, so in the S-built specimen, we have only the peaks of copper. So we have a solid solution of copper. After solution annealing, we have small peak. You can notice a very small peak of zirconium metallic, and even smaller and not well visible, I think, in the slide, a small peak of zirconium intermetallic after a direct aging at 580 degrees centigrade. So that means that if we perform solution annealing, we precipitate phases, and we have less hardening effect during aging. After that, we tried to perform a direct aging, changing the temperature, because having noticed that the behavior of the additively manufactured specimens are very different from the traditional ones, tried to perform aging at a lower temperature. So we age also at 450 degrees centigrade. So what we can see is that if we decrease aging temperature, the hardness of the alloy increases, reaching values in the peak of the hardness higher than 200 liters. So obviously, what we can think by observing those curves is that if we use a lower aging temperature, we have formation probably of smaller, probably nanometric intermetallic particles that are more effective in hardening, in increasing the mechanical properties of the alloy. So, as a conclusion, we can say that obviously additive manufacturing process of copper chromium zirconium alloy must be improved in order to reduce defects such as cavities and lack of fusion that obviously affect the mechanical behavior of the alloy. That the very high cooling rate characterizing the additive manufacturing process produce the formation of a supersaturated solution that must be directly aged, and that lower aging temperature, we tried only for 150, but we would try also other temperatures. So lower aging temperature determine the formation of smaller compounds that increase the mechanical properties. So thank you for your attention. It depends also on the printing parameters, but the problem is that when you produce by additive manufacturing is like if you do welding passes, no subsequent welding passes, very, very high cooling rates. So these affect the microstructure. You cannot change that.
Yeah. Yeah. Okay. Yeah. Thank you, everyone. I'm Xiaopeng Niu from China, a PhD student now studying in Sapienza. Now, today's topic is defect-tolerant fatigue assessment of AM materials, the side effect, fatigue, getter, and problem aspect. So about the background, since the industry evolution, the fatigue problem have entered into people's vision nearly 200 years, and more than 19% the mechanical failure is about the fatigue. So the modern structure requires higher reliability and accuracy and complex select design from the infinite life design, safety life design, damage tolerance design. We gradually found that the material component is always the impressionable defect. The traditional to the AM materials, all they are especially for the AM materials, AM attract a lot of attention because he has a lot of advantages. However, the AM have larger defects and poor fatigue performance. So many guidelines and roadmap are written, and the international organization try to achieve the standardization, including the design process and materials, the qualification and the certification, no destructive elevation. In the process, a lot of problem must be considered. For example, the side effect from a small sample to the large structure, the notch effect from a small sample to the complex structure, and the probability. So the former two problem, we can get the structure performance from the small sample, and the probability can let us know the lower boundary performance. About the side effect in fatigue, it means the influence of defects on the fatigue limit or the strength. According to their sources, they can classify into three types: the statistic side effects, the numerical, the technology. Maybe the statistic is the most well known because, for example, the fatigue strength of the material will decrease with the sample size. So we try to simplify the types with the statistic and the technology aspect are uniformly attribute the defect size variation. So we use the extreme value statistic to address the side effects. This approach firstly use the earthquake, the rainfall statistic, then it is used in the fatigue. For example, the fatigue life or fatigue strength or the defect statistic. The Gamble filter and the Weber distribution, they are the extreme value distribution based on the different shape of parameter. So based on the smallest extreme value and the largest extreme value, we can there are two strategies approach to deal with the size effect. The weakest link and the critical defect approach. The weakest link approach assume the fatigue performance of every element is in dependent identical distributor, and the whole material performance depend on the weakest part, just like the short plate effect and the series system. So if we know one element fatigue performance, so based on the joint probability distribution, we can go the whole one. Doesn't need the defect data, but pure statistic approach. So another one is the critical defect approach. This approach is firstly get the defect information, then use the fatigue model to get the fatigue strength distribution. There are two approaches. The block maximum gets the this approach gets the defect information by using the fracture surface observation, and all the defect will be counted. The next is the peak over threshold using the CT scan. Only the defect with larger than a critical size will be counted. So the two approach, weakest link and the critical defect, they need to determine the a reasonable control value. So firstly, the crack initiator always occurs the highly stressed value, such as a notch. Then because the surface defect is more harmful than internal one, so we choose the coupling region as the control value. For some complex structure, we can using the ANSYS to filter the aimed element. So in addition to the size effect, we also focus on the fatigue scatter. We can see this picture. There are 2-3 group samples with different size. Every group have their own fatigue scatter, and the difference between the different group average value is the size effect. If we want to get a performance structure from a small sample, we should deal with these two problems. Also, so we use the derived distribution and the fatigue model. We can get the fatigue stress distribution, and we propose the stress alter factor. Actually, it's the relation between fatigue stress to a derived fatigue stress. We use the factor to this factor is substitute to the conventional equation. We analyze the knee point, the fatigue, the baseline curve, and particular limit. Maybe some details are ignored, but we hope to get a simple design curve equation, just like this. Finally, we add some other factors, for example, nurture or random loading. Then we use the loading length reference. We can relate the safety factor and the reliability. Of course, we only give this equation. It's just a framework. We needn't. We don't have completed this work. For example, the nurture fatigue factor KF is difficult to determine. We can determine it by testing or other energy or critical distance approach. So this is a conclusion. We summarize my work. So thank you very much. Next. Sure. Thank you, Mr. Chairman, for your introduction. I'm Pietro Magarò from the University of Calabria, and the title of my talk is Multi-Scale Approach for the Estimation of Strain Response of Laser Powder Distribution Light Structure. So today, 3D printing gives the possibility to obtain complex geometry components that have the big advantage of lightweight with high mechanical properties, high specific strength, high energy absorption. But often due to the high cooling rate of the melt pool, of the melt pools, fine-grained microstructure usually characterizes the printed material if compared with the conventional ones, and in particular, grains tend to be elongated along the building direction. This often imply an isotropic behavior, so often different mechanical properties of the strain response can be observed in the two characteristic direction, that is the direction perpendicular and parallel to the So in this research, conventional stainless steel powder was used to produce both bulk bond samples, the lattice bond samples, and in particular, the latter are characterized by 8 degrees of consequences of ultrasound, with equal size of 6 mm length, and density of 20%. And in that conditions, the first diameter is equal to 0.2 millimeters. So in the same slide, I reported also the main process parameter for the printing process. So at the beginning, a numerical model was calibrated the geometry of the lattice sample that was obtained starting from the microscope data, and the microscope plans are carried out taking a box resolution of 52 microns. Regarding the mesh, the tolerance was set equal to 15 microns after for the mechanical properties of the printed materials, this latter was measured directly using simple tensile test carried out on the bulk bond samples in order to measure the young modulus and the plastic branch of the
observed a very non-existent match between the empirical and experimental results in terms of the force displaying curve of the lattice band. This result was attributed to the very complex structure of the due to the very small dimension of the nodes of the lattice sample with that are characterized by the presence of a very structure, with the presence of involutions, with the presence of the processing forces and so on, that modifies significantly the response of the material. So an in situ approach was adopted in order to locally estimate the material properties within the material based on the Oliver-Var method, so based on the non-indentation technique. But Oliver-Var method allows to directly measure the Young modulus of the material, starting from the period of the contact, obviously, while the yield strength of the material was estimated, okay, was estimated from the assumption that there is a linear correlation between hardness and yield strength for the conventional integrated material. Comparing the hardness measured by the non-indentation techniques and the yield strength of the tensile test and the bulk of bond samples, this constant of proportionality was estimated in order to estimate the yield strength of the printed materials in the locally in the truss and in the nodes and in the two characteristic planes, planes perpendicular and parallel to the finally, for the estimation of the branch of the maximum curves, this latter was modeled using a power law equation to our characteristic exponent with strain hardening exponent that was estimated using a literature model by Diane that correlates the main characteristics parameters of the non-indentation curves with the characteristic parameters of the sigma epsilon so the Young modulus, the reduced Young modulus of the non-indentation, the yield strength, and the strain hardening. So comparing the mean indentation curves obtained from 100 indentation measurements in each zone, we can observe as can be found in the private sector, while in the parallel section, systematic reduction and that can be so using this, the characteristic parameters, curvature of the load impact, the slope of the load impact, the maximum the residual penetration depth in the model version introduced before, the stress strain response of the material was estimated, and also in this case, non-negligible differences in the 4 zones analyzed was so using that model, that material constitutive model in the numerical simulation, we observed a very good fit between the experimental and using the strain responses because that's what represents the weakest region in terms of the materials. Their properties mainly dominate finally, also locally, the model was this approach was validated to compare strain maps measured with the digital image correlation. Strain maps computed on very the better fit was observed to get material properties. So, in conclusion, the actual geometry of the printed and this geometry was while the constitutive that can made part of content that cannot be used in order to calibrate a spherical model. So because the mechanical properties of abstraction and locally characteristics of the sample, node and rust, and in both characteristics. And this approach was allowed to well predict the experimental response of the material, and this approach was also validated combining the strain mass, the experimental digital image correlation with the strain maps obtained from element. Thank you for the attention. Yeah. How long do you? Because it depends on the conduct of the material. The cross speed of the transverse of the machine would set equal to 1 millimeter per millimeter. How long? Okay, experimental. Okay, the solution time. The experimental time is around 6 or 7 hours. Depends on the dimension of the mesh and of the and of the quantity of run present in the Thank you.
Champagne. No, sono abituato. Okay. So good evening, everyone. I am Alberto Ciampaglia from Politecnico di Torino, and today I'm presenting you a data-driven method for predicting the fatigue response of the additive manufacturing metals from the process parameters. I've been developing this method together with Professor Tridello and Professor Palino from Politecnico di Torino and Professor Berto for Sapienza University. So, as you know, the fatigue response of metals can be modeled by well-known formulation, while the fatigue strength at a finite life can be computed starting from the fatigue limit of the material. So the fatigue limit itself, according to the Murakami formulation, can be described by this formula, where we can distinguish two main factors. So the first one is the vigorous hardness, that according to Murakami is related to the microstructure of the material that we are characterizing. And second one is the area of the defects. So when we deal with the additive manufactured metals, both the microstructure and the defects are dependent on the process parameter itself. So from there, the idea to model the fatigue response of the additive manufactured metals starting from the process parameter itself. To do that, we use the machine learning approach. So in machine learning approach, you need a database. So we have collected a bunch of experimental data on process parameter and the fatigue response of aluminum alloy printed with additive manufacturing. And we used a neural network to find the relationship between the process parameter and the fatigue response. So the neural network is one of the most common machine learning architecture, where the input is propagated toward the output through some stacked layers. Within every layers, we have some neurons, and within the neurons, we perform a very basic operation,
where the inputs are weighted, summed up, and passed through an activation function A. So the parameter of our neural network are the W and B, and these are trained with a training data set. So a bunch of data where we know, in our case, the process parameter and the fatigue response. So the advantage of this method is that neural networks are universal approximators, so you can approximate any function if you have sufficient amount of data. So this can be a restriction in terms of experimental mechanics, and also the prediction could be physically inconsistent because we do not predefine the model before the modeling itself. So there is a different approach that can be used to overcome this limitation of neural networks, that is the physics-informed neural network. So if we have some knowledge that puts in relation the input and the output of our model, we can use this knowledge and infuse to the neural network and build a physics-informed neural network to enhance the predictive capability of this tool. The main advantages when we use this approach is that we can have good prediction with a smaller data set, because we basically confine the domain of the solution, and we can have some physically guided prediction that is strictly fundamental in science, of course. So the way we did that, so we propose a modified architecture of our neural network to use the physics knowledge that we have seen before. So starting from the processing parameter of the selective laser masking process, we divide it in two different branches. So a first branch predicts a microstructure latent variable, and the second one predicts a defect latent variable. Then these two latent variables predicted by two different neural networks are fitting a second block where we mimic the Murakami equation. So we compute a ratio between this microstructure latent variable and the defect latent variables and combine it with the number of cycles to predict the fatigue strength itself and get the fatigue response starting from the process parameter. We trained both the standard neural network and physics-informed neural network using a loss function as a mean square error loss function. And we achieved a 20% better performance and better accuracy of the physics-informed model. That is shown here, where we compare the prediction of the neural network on the x-axis with the experimental observation. Of course, the fatigue response has some scatter that these deterministic models cannot capture itself. So there is an uncertainty band of 50 megapascal that has been that is shown in the picture. But overall, we can say that this method can predict the fatigue response of this model under different printing parameter, even with the resulting curves are very different between them. And another advantage of this architecture is that the predictive capability is also better behind the observed domain during the training, because we're infusing some physics that is preserved even when we are predicting outside our dataset. So for example, if we take a look at some dataset where we have some data until 10 to the 6th number of cycles, we can see that using our method, we will have a reliable prediction or a physics compliant prediction even in very high cycle regime, because there was some data from the very high cycle regime and neural network could learn the relationship between the printing parameter and the response at that regime. And this can also be used. We have been validated also this network against some dataset that was not present in the training dataset, of course, where one parameter for the printing process was unknown. And by varying the unknown parameter, that is the beam diameter in this case, we get a band of the prediction. And we can see that the experimental data falls within the bands with an acceptable accuracy. And this tool can also be used to investigate the influence of one single parameter on the fatigue response. And again, we have tested our network again, an experimental dataset where a specific design of experiment was designed to study the effect of the edge distance on the fatigue response. And we compare on the left the black box approach where we have a standard neural network, with the right our proposed neural network with a physics-informed approach. And we can see that neural network is able to capture this trend accordingly to the experimental data. So this means that even if we don't have a well-designed experiment properly thought to explore the effect of this parameter on the fatigue response, learning from a big data set with sparse data, the machine learning approach is able to approximate and predict the interaction of different parameters anyway. So arriving to the conclusion, what we have achieved with this project is the development of a physics-based data-driven model that can predict the fatigue response starting from the printing parameter. So we believe that is a useful tool in the end of the designer that need to set the printing parameter beforehand before printing their part, with an overall good accuracy that can learn the interaction between the different parameters and how they affect the microstructure and the defects, and as consequence, the fatigue response. And fatigue curves resulting from our method result physics compliant with the physical trend that we know for the fatigue. So due to the time constraint, I didn't go through the details of the method, but an article has been published about this methodology that you can find scanning the QR code on the left. On the right, there is QR code for a special issue on machine learning for fatigue design that our research group is managing on MDPI. So thank you for your attention. This one or okay. Yeah, that's us. Yeah, basically, yeah. It's kind of a modular network learning the parameter of the equation that is mimicking somehow the Murakami equation. Yeah. Yes, so yeah, we kind of infuse the physics knowledge by modifying the architecture itself and mimicking some known equation rather than adding some physics-based laws like in the most common approaches, let's say. Yeah, yeah, you're right. Thank you for your question. It's, I guess we collected about 20 articles and overall there were like 800 data points. Yeah. Yeah, but all the data were available in literature. So. No, we did not study that actually. Yeah, not yet. No, actually, we directly start from the process parameter. So you will find all the parameters that you can see in this slide, together with the heat treatment parameters and the fatigue response described by the number of cycles and the fatigue strength. Yeah, this is a latent variable that are kind of predicting the effect of each parameter on microstructure and defects. So the basic idea is that in future, this same architecture can be trained independently, each branch, if we have some data about defects and hardness itself, and we can still combine it with the knowledge that we get from this training, let's say. Thank you very much. Thank you for your question. Oh, okay.
Thank you very much. The work that I'm going to present is dealing with the wrinkling of soft membrane created with additive manufacturing, and is a study in cooperation between NTNU, University of Parma, and Sapienza University. I'm going to present this work on behalf of Ranim Amayed. So here you have an index of the presentation with the 5 steps in our research, but I would like to rather present what is the motivation behind this research. So nowadays, still nowadays, the leather industry is employing a high quantity of resources and also is creating several waste that may harm the environment. So there is still the need to make more sustainable this type of industry. And we investigated the possibility to use additive manufacturing technique to create a leather-like membrane with the scope of reducing the resources employed, speed up the production process, and improve the quality control. And for this reason, the research questions that we had in this work were related to the creation of a leather-like membrane, if it's possible, of course, with this technique, which type of material can we use, and how can we reproduce the wrinkling effect that is a daily effect that we observe on leather material. So here you see the leather as material that can be simplified with the grain at the surface that is constituted by a short fiber, collagen fiber, and then the corium part that is under the surface of the leather. Similarly, in our analytical model and numerical model, we simulated this material with a 2-layer membrane constituted by the film that is resembling the grain and the substrate that is resembling the corium. And then we investigated in literature the type of material to use with additive manufacturing technique to resemble these 2 layers. And so we selected the PLA, this thermoplastic, to create the film layer, and the TPU, the thermoplastic polyurethane, to create the foundation. Why? Because the PLA is the biodegradable, and of course is very cheap as material. So theoretically, if implemented at large scale, can reduce a lot the waste or can be recycled. And then the substrate of TPU, because it can resist to abrasion. In terms of technique, we use in our study this B-material printer. Even if we were able only to print at the end, because of some issue, sample made of PLA. And of course, we use the G-code and the software SSI and the full control to print this specimen. We did a quality check on the specimen we produced, looking at the filament adherence, the extrusion rate, and the pattern sharpness. In terms of printing setup, you have here the summary. So our PLA had the thickness of 0.15 millimeter, the layer, while the extruder wide was 0.3 millimeter. The temperature of the extruder range between 200 and 210 from the specimen to the raft, and the bed temperature was 60 Celsius degree. Concerning the experimental approach that we implemented, in order to see the wrinkling effect, we did compression test, of course, and we followed the let's say the guideline of the standard ASTM, both for the production of the 5 specimens done in PLA. So we produce these 5 specimens with a prismatic shape, prismatic geometry with this dimension.
And we perform the test using an instrument model 1342 machine with the load capacity of 100 kilonewton and a test velocity of 1.3 millimeter per minute. Concerning the analytical approach, you see here a sketch of our P-layer membrane. So we have a thin skin with a depth of equal to H and a foundation that is much wider. So the hypothesis here is that we have a perfect bonding between the skin and the foundation, and that we don't have any shear stress between the skin and the foundation. In this illustration, you have lambda, that is the sinusoidal deflection pattern, let's say, that show the wrinkling effect. That happens when we have a compression force that is larger than a critical value that you may express in terms of lambda, critical lambda. As you can see from this formula, this critical lambda depends only on the thickness of the film, so of the very thin skin in our membrane, and by the property of the skin and the foundation. Concerning the numerical method, the geometry that we reconstruct in the numerical simulation had a thickness of the skin layer, very thin, equal to 0.2 millimeter, and a foundation instead very large, in a ratio between the skin and the foundation equal of 1/50. The input in the model were obtained by our experimental test concerning the property of the PLA, while the property of the TPU were provided by literature. And with the numerical simulation, we performed the buckling analysis and the nonlinear analysis. I go to show the result. So concerning the first result, I want to show the outcome of the printing stage. So you see here the 5 specimens that we produce with the PLA material. And then we did this quality check on the filament adherence, the extrusion rate and pattern sharpness that demonstrated that the quality of the specimen was good. As well, we perform a quality check in terms of dimension of the specimen, comparing our 5 specimens with that one described by the standard. Here, the result of our test, compressive test, you see in this figure, in this illustration, the compression that we obtain at the end of the test for 4 specimen over 5, and all these deformation are comparable, are similar. You see here the value of the compressing strength and the elastic moduli of these 5 specimens, and you can see how the deformation were visible after the enrichment of the yield strength. Concerning the final result, that was the comparison we did on the critical wavelength of the wrinkling effect, we compare our result from numerical simulation that you can see here with the orange histogram, the result that we calculate with the analytical model inserting the input data for the PLA and the data for the TPU from literature, and then instead the value of critical wavelengths of leather-like membrane as we found them in literature. So you can see that the critical wavelength is comparable and is of the order of magnitude of millimeter. On the right, the buckling analysis results and the result of the nonlinear analysis that show the wrinkling effect with different load increment. To conclude, what we can say is that additive manufacturing can be a technique that can be used to make more sustainable the leather industry, because it can reduce, of course, the production of waste, and it can really speed up the process of the production of leather-like membrane. We have tested some materials, so especially PLA, but more research is needed also with the specimen that can really resemble a B-material membrane. And from our result, we observe a similar comparable critical wavelengths between the analytical method, numerical, and literature. So thank you very much for the time. Thank you.
Non sembrerebbe. I don't think it is. Yes, the remote presentation are this morning. Yes. Yep. Let's start. Okay, it's fine. Okay, good evening, everybody. I'm Carlo Burciagnota, postdoc researcher from the Department of Mechanical and Aerospace Engineering at Polytechnic Torino. And my talk today is about two methodologies that we have developed and implemented for the fatigue design through topology optimization. We have seen also through other presentations that the presence of defects affects the fatigue performance of components. And this is particularly true for additive manufacturing components, which are characterized by a significant presence of defect within them. And in the design of topology optimization, that is the usual tool used to design the additive manufacturing components, the influence of the defects on the fatigue response is not accounted. As shown with the flowchart on the right, usually only a static constraint is imposed within the problem, then the effect and influence of the defect is characterized after the production of the component through Microsoft T, for example, so obtaining the defect distribution. And then the fatigue response, the fatigue step is verified. And if it's not, we have to redo the step. And so we have to redesign the component and reproduce them. So the goal of this activity is to account for the fatigue strength of the component within the topology optimization and to accordingly formulate the problem. To do that, we consider two methodologies that we developed. The first one is called the marginal PSI curve. Here are some mathematical details. It accounts for the experimental data that is typical of fatigue data. The main thing that I want to highlight is that the cumulative distribution function of the fatigue life is conditioned by the defect size, where the defect size here. And which means that according to the size of the defect, you have different response of the fatigue life. And also by modeling fatigue life, the defect distribution through the largest extreme value distribution, we can take into account different scale of the specimen of the components. We can scale the largest defect that you find in the specimen to the largest defect that you can find in the component. And the other approach that we use is the test gradient method, which instead does not see the defect distribution, And in this method, the component is seen as an assembly of several uniformly stressed subvolumes. Each subvolume is then subjected to a specific stress. And according to the Pascal model, we have that the larger the volume, the smaller will be the fatigue life. And also, you can say that the larger the volume, the smaller will be the fatigue life into the weakest state. So then, by modeling the fatigue life with the wide distribution, you can come out the fatigue strength. And the two methodologies, the idea of the two methodologies is that we define the number of cycles at which we want the fatigue strength. We define the quantile for the proper curve, and then we can get out the stress amplitude and fatigue strength. Then we implemented that into the topology framework. So adding to the fatigue static constraint, the class for the static loading conditions, also a fatigue constraint for the fatigue loading conditions. And however, the two methodologies have that fatigue strength varying with the volume. As for the first methodology, the largest defect size varies with the volume of the component, and in the second one, you have the stress gradient and stress function varies with the volume of the component. So at each iteration of the topology optimization, you have that you have to calculate. And so you need the iterative procedure. You start with the value of calculate the quality, perform optimization, then update the fatigue value according to the new volume that you have obtained, and then check the value are smaller than an epsilon value. And so if that's true, you have your optimal design. Otherwise, you have to redo the optimization until you converge optimal results. Methodologies for the this was made of alloy. For this, we have the experimental data that are reported here on our glass and Gaussian specimen, and here reported also in the TSM process in the two methodologies. The design is performed in upper mesh. In red is the design domain, and in gray you have the non-design domain part. So we selected the quantile of fatigue strength according to the methodology. And here are the results. The contour plots of the stresses that we obtained. On the left, you have the two topologies obtained with the defect distribution method. The difference between the two is based on different points of the volume that you consider at the end of each optimization run to perform. The first one, the one at the top left, you have that we consider only the volume that experiences at least 90% of the maximum stress, while the one in the middle consider all the volume optimization. You can see that the quantities are pretty different one from the other, and also here the results obtained are very different, and also the maximum stress that they experience are different. One is about 80 megapascal and the other 50 megapascal. And instead here you have the result of the on the right, the result of the stress gradient method. And you can see that the topology is very similar to the one obtained with the defect distribution method that considers all the volume. And in this figure, I represented the variation of the volume distribution of the volume of the stress, and we started from the first iteration, the one blue, and then we shifted to some value, the one reported in gray, until the convergence was reached with the network. So in conclusion, with this work, we compare these two methodologies for modeling the fatigue results with the finite life range. And the two methodologies are able to account for the experimental factor. We implemented that in the technology framework, the NIPERMES, and applied for the design of the end control. And the main conclusion is that the method is strongly dependent on the force of the revealed volume. It is an arbitrary force. While the precedent approach leads to really good results that are very close, very similar to the defect for all the volume. And also this was remarkable that this method, the stress gradient method, not require complex analysis of the defect population. It accounts for the size effect within the process. And so more suitable for industrial application. I thank you for the attention, and as my colleague has done, I would like to invite you to this special issue about the advances in statistical analysis of fatigue data in materials. And thank you.
Thank you very much.
Yes, sure. Thank you.